Okay, is my screen visible?
Yes, sir.
Yes.
Yes,
Oh,
sir.
good. Okay, so today we have quite a few things to do. To start with, I will give you a very brief, I would say, guided tour to these things, basic Unix commands, which you should know. By this time, I hope all of you are acquainted with Unix, in particular Linux maybe. So these Unix commands are applicable to Linux because it's a Unix-like system. And then we will switch to an introduction to the make utility. Okay. After this, AG will explain today's assignment. So it may be going to be a long day. So without further ado, let me start. Okay, so let me go to full screen. Yeah, so as I mentioned, you should have by now installed and worked with Unix. And most of the things you can do by using your file, what is that called? Using a file manager or some kind of thing, and by clicking things like editor and all that stuff. But these things are actually not good in the sense that they all require your manual intervention, like clicking somewhere and all that stuff. Suppose I want to see a file, so of course you can use an editor. And if I want only the first 10 lines of the file, so I can open the editor, make a copy of the first 10 lines and paste it somewhere else, say like in another file. That requires your manual intervention, like opening an editor, highlighting, copying, saving that thing in another file. So nearly, I would say, this is not an automated process. Okay. But if you open a shell and run a set of commands, okay, this can be done automatically. So some command that chooses first 10 lines of a file. Okay. You may say that this is also some kind of interactive thing because I have to type that command, but the point is that you can actually write this thing in a shell script, possibly a long one, and depending upon whatever you have written in that script, commands will be executed one by one. It no longer requires your manual intervention. This is one of the motivations why you should learn the Unix commands. And the second thing is that, of course, you should get comfortable with this Unix system, with the shell and other things. So I would very briefly go through this because most of you, I assume, already know it. And if you do not know, whatever is written, you try yourself and get acquainted with the, I would say, most useful commands. Anyway, so first of all, you should know how the files and everything is organized or are organized. So Unix supports a directory tree, which starts from this so-called root directory, which is denoted by slash. Okay. And under slash, you will see several subdirectories like boot, dev, etc, home, lib, okay, and so on. Under each of these, there may be files or further subdirectories. For example, by default, the users have their home directories under this slash home. For example, if you are foobar, your home directory will be slash home slash foobar. Under that, you may create several subdirectories like doc, image, systems programming lab, tem, And under the systems programming lab, you may have several subdirectories like books, prog, slides, tests, and so on. Okay, so I have not definitely shown the entire tree, but the idea of organizing things, the entire file system into a or as a tree of directories should be clear from this example. Okay. So this is the root under this directories under this, and so on. So this kind of tree structure we follow in Unix. Okay. So what does a directory consist of? So first of all, subdirectories, as you have already seen, and there may be text files and like C source, text documents, program output, scripts, and so on. There may also be some binary files, which may be executable files like a.out. There may be images, printer files, and so on. And there may also be some special files like sockets and symbolic links. You do not need to understand much about these things for the moment. And this is also an important thing. Every directory contains two subdirectories, dot, which is pointing to itself, and dot dot, which points to the parent directory. Okay. And it is assumed that the parent of that root directory is that root directory itself. Okay, if you do dot dot there, or if you want to go to dot dot from the root directory, you will stay there actually. Okay. And files or directories with names starting with dot are called hidden files. In particular, these directories are hidden. Why hidden? Because a directory listing of the files without the so-called -a option will not print this files or directories starting with dot. Okay. And also note that whenever you log in, you enter your home directory. For example, it's the default behavior, home foobar. And this is another thing which you will learn little more comprehensively later. In Unix philosophy, everything is a file, including directories, sockets, symbolic links, everything is a file. Anyway, so how to see, yeah, any question?
Yes, sir, I had a question in the last slide.
Yeah.
Sir, exactly what is the dot command means? How do we apply
It's
that
command.
command?
It's not a command. It's a directory. It's not a command.
So this is dot is the name of the file. Like,
Okay, let's look at this. If you are here, okay, /home/foobar/spl, dot means the same directory. home/home/foobar/spl, and dot dot means its parent directory, that is /home/foobar. That's it.
okay, sir, understood.
Okay. Oh. These are two special directories. Okay.
Sir, is Foobar a default one or is it just for example?
In every Unix directory, you will find these two files, directory type files, dot and dot dot.
No, sir, I'm asking that home Foobar, is that Foobar and default one or?
No. This is the typical convention followed by Ubuntu, but you can override it. Okay, it may be anywhere else.
No, I think he's asking Suvari, no, foobar is just an example. Not in every machine there will not be a directory called foobar.
I assume that there is a user called Foobar and two other users like Atpug and Sad. Okay, there may be many users, many other users, and they may be under several under different subtrees. That's possible.
Sir, we are already in a directory. Why do we need a dot subdirectory which is pointing to itself?
Okay, I will come to that maybe a little later. It's typically not needed, but this is a Unix convention. I mean, something pointing to itself is perhaps not very, I would say. But sometimes file names are given, files or directory names are given related to dot. Okay. Okay.
It's basically a symbol for the current thing if you have to refer to itself, like you said ./a.out.
Yeah.
So it's how do you specify that look in the current directory? So this is for the current directory of the dot basically.
Yeah. That's also important because if your dot is not in the current path, of course, this is another example. If you want to set the current path to include always the current directory, you should include dot in the so-called $path. Okay.
Okay, sir.
Okay. So there are other applications anyway. Okay, so I will not go through the details of this command. So the directory listing can be seen using the command ls. Okay. In particular, ls minus l, this is not 1, this is l. Font is bad. Minus l. Ls minus l essentially gives you a long listing. And there are many other options. So these things I leave to you to really understand what these different types of options are doing. So I would say, work it out. Okay. And as I mentioned, every directory or file is named in two different ways. One is called the absolute name. So you start from the root directory / and then keep on moving down the tree and end with some directory, and that will be a directory, or if you have something, a file like this. Okay. So these are called absolute names. Home, foobar, SPL, prog, assignment, /a1/src/makefile, something like that. Okay. And there are two types of relative names. One is relative to the current directory, like ./a.out. And if you do not write /, then it is always assumed to be /. Okay. So if you simply say a.out, it means it's in the current directory. Okay. So this is something related to the current directory. You can also go to something like ... go to the parent directory, and after that you follow. Okay. Move down the tree. So this is another relative name. Also, you can specify these resource names relative to the home directory. So tilde essentially implies your home directory. If you are foobar, and if your home directory is in /home/foobar, then this is basically /home/foobar/spl/prog and so on. And if you are referring to some other user, you are foobar, but you are wanting to look at whatever is there under let's say SAT's home directory, then you can say ~SAT. You can also say ~foobar here. If you are foobar, tilde means ~foobar. Okay, so these are two relative ways of specifying file names. Okay. Yeah, so I don't think there should not be any. I don't think there should be any confusion in this. Okay. And for everything that I talk about in this set of slides, you should go ahead and check that things are working as mentioned here. Okay. Okay. Now, if you, for example, make a long listing ls minus l, we will see several things, minus, 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 dd. So this minus basically stands for, this is a regular file. D stands for it's a directed type of file. And if it is symbolic link, you will see something else. If it is a socket, you will see something else, and so on. This is followed by 1, 2, 3, 4, 5, 6, 7, 8, 9 characters. Okay. So these 9 characters essentially tell what kind of permission different users have for accessing or executing or even overwriting these files. Okay. So in order to understand this maybe I will take a little bit of time. So there are 3 types of user. The user who owns the file, this is called U. Okay, and users often belong to groups. Not often, they always belong to groups. For example, you can see that the username is SAD. This belongs to the group faculty. Okay. This is what is meant by this. And any other user is called other, O. So there are three types of users: the owner, U, other group members as the owner, okay, same as the owner, that is G, and all other users, this is called O, others. And for files, or for each of these U, G, and O, there are three types of permissions: read permission, write permission, and execute permission. Okay. And these meanings are obvious for regular files, but for directories, they have slightly different connotation, meaning write permission is clear whether you can write or create new files in that directory. But there is a fine difference between read permission and execute permission. So the directory is not an executable file. What is meant by execute a directory? So this is the convention. Read means you can view by ls what is there. Okay. You get the listing of all the files in that directory, and execute permission allows you to go to that directory and access, means open or execute files in the directory. Okay. But if you do not have read permission, if you only have execute permission, you cannot view the listing of files. So only if you know some names of files that exist, that reside in that directory, you can open it or execute it. Okay. Okay, so with only execute permission, you cannot see the directory content using ls. That requires read permission, and other things will require execute permission. For example, suppose that SAD is from group faculty. Athpug is also the same group. Okay. And Foobar is a student, so he belongs to the group student. Okay. So this says that SAD, who is the owner, the user, he has read permission, write permission, execute permission for a.out. Nobody else has any of these permissions. In particular, only SAD can execute a.out. Okay. If I now look at makefile, it says that SAD has read permission, write permission, no execute permission. Athpug also has read permission, write permission, but no execute permission. And Foobar has only read permission, cannot write. Okay. Similar thing here. Even Athpug cannot write this file, overwrite this file, because this W, although Athpug belongs to the same group. Okay. And so on. Okay. So I would suggest you change the directory permissions and see what people can do. Okay, with these different configurations. So for example, you are Foobar. So if I consider this shared directory, you can say ls minus l shared. Okay. Okay, ls minus l or whatever, ls whatever the other options, home, this. You can see the content, but you cannot access any file in that directory. Okay. Whereas here, this is you have execute permission, but not read permission. So you cannot see the directory. But if you know a file name in that directory and have read permission for that file, you can view it. Okay. Okay, so this type of permission thing, I think you should know. And then the question is how you can change. Sir? Yeah, tell.
Sir, what is meant by reading a.out?
It is not, I would say, reading a.out. Yeah. For example, there are many situations where you may, for example, you want to read it. To start with, if I want to see what kind of file a.out is, then there is a command called a.out. You are not executing anything, but there is some signature in your files. You want to see whether it's an ELF type file. So there is a command called file. You say file a.out, and it will read, or it will try to read that signature from that a.out. And if it sees that yes, it's an ELF executable, it will say it's an ELF executable. It's not executing it. Okay.
Okay, sir.
Okay.
Sir.
And also, if you have something like a binary reader, you can read a.out. Yeah.
Sir, what is SAD here?
SAD is a user.
Okay, sir.
SAD is a user. Foobar is a student user. Athbook is another faculty user. Okay, these two are faculty users. Foobar is a student user. Okay.
Sir, what is this D at the start, like DRW?
T is directory.
Then only some of them have a D means a folder inside a folder, like something like that.
It's a folder inside a folder, yes.
Okay.
That is possible, right, in a tree structure.
The terms directory and subdirectory in the context of Unix is the same as folder and subfolder in the context of Windows.
Okay, sir.
Yeah. Okay, so chmod is a command, change mode, by which you can change these modes, and only the owner can change it, and the super user, the root, can do anything. Okay. So you just read how to do it and try it yourself and find out that things are happening this way, whatever is written here. Okay.
Just one word of caution. So at the beginning, when you are trying out things, create a completely new directory. Doesn't contain anything important. Create a new file inside it, just a simple text file, and then change on those directory and files. Don't try it on standard Linux directories that already exist, because if some of them gets messed up, then you have to restore it back and so on.
But possibly without super user permission, they cannot do it.
Right. No, you can always restore, but then they forget what they have changed and all. Many of them will be logged in as root only.
Yeah.
So just at the beginning, just try it on some new directory, new file that you create. So if anything happens to them also, it doesn't really matter to you.
Yeah, and avoid not only the system files, also your important files. Do not play with your important files, like assignments and things. Keep these things safe. Okay. Okay, so changing permissions you can do by chmod. You can even change owner. The user, the super user can change owner using chown. Anyway, you will eventually figure out how you can do it. You can go to a directory using cd. You can create a subdirectory by mkdir, make directory. You can remove a directory using rmdir, and you can remove an entire subtree rooted at this directory using rm-r, remove recursively. You will often also use this with rm-rf dirname. Okay. So you learn this command, cd, mkdir, rmdir, rm-r, and all that stuff, but never try to, I would say, always be cautious that you are not deleting any important files. You can experiment with things, but take care. Okay.
Sir, can you explain that last command, rm-r?
Okay, let me once again go to these. Suppose for some reason you want to completely remove this subdirectory. Prog may have, this complete tree rooted at SPL. Okay. Prog may have further subdirectories, slides may have further subdirectories, and there may be subdirectories, and maybe a big tree here. Okay. And if you are sitting in foobar and you say rm-rf SPL, then this entire thing will be lost. Okay.
Sir, won't that happen even if we do rmdir SPL?
RM?
DIR.
Oh, okay. So that's what is written here. If something is, rmdir lets you remove the directory, provided that you have write permission, of course, in the parent of dirname, otherwise you cannot do it. And this is completely empty. rmdir is just remove the directory. Okay. Not anything under it. So if there is something under it, RMDI will simply fail. It will say that the name is not empty.
So
Okay.
if we have some files in the directory, we cannot use them.
You cannot delete that directory. Okay. And recall that this RM-R or RMDIR or whatever you are doing, so these things are not, I would say, moving your directories or files to something like trash. If they are removed forever. You can never retrieve them again. So be very careful. Okay.
Sir.
So it's like shift delete. Okay. Okay. And for files, you have.
Sir.
Yeah.
Sir, in Windows we have this program files folder where by default everything gets installed. Do we have something like that here?
It's usually under user bin, and there are some system directories, user bin, user local bin, things like that. Things are installed there. Whenever, I don't know whether you have any experience in installing new things. Okay. The system things usually go there. Okay. And if you have some, what is that called? Some Debian file, .deb file, they will be installed there. But it's written where these things should be installed in that file itself. Okay. Okay. So the CP copy file this to this, move. If it is also a file, it's basically a renaming of file 1 as file 2, or you can also move a file to a directory, a new directory. Okay. And you can have multiple things here, but if you copy several things, you cannot copy several files to a file. The last thing should be a directory. Okay.
Hello, sir.
Yeah.
Sir, what do you mean by file here? Like, is it a text file or something?
No.
What's that?
No. By file, I mean a regular file, something like this, which has minuses here. They are not directories, but of course, for certain things also work with directory. For example, you can move a directory to another subdirectory. That is also allowed. Okay.
It is just what you know as a file in Windows. As I said, the notion of file, directory, subdirectory is same as in Windows file, folder, subfolders. If you know Windows, just map it there. A file is a file. Can be text, can be binary, can be anything. It's not a folder or a subfolder. Okay.
Okay, sir.
Just a file.
But sir, how can we copy a file into another file? Just like a text
How
file.
do you do
file
copy and paste in Windows? When you do copy and paste, what happens? You copy the file, create another file.
Yes.
Same thing. It's
And
just allowing you to specify. If you do copy and paste, by default, the name comes as the file name -copy. Here, it's allowing you to specify what do you want to call your destination file.
And move is kind of renaming.
Yeah, move is the same as renaming. What is the old name? What is the new name?
Although this move is not like that. You basically cut and go to the directory and paste. This is similar to that. Okay.
Sir, can you show some of the steps with your terminal?
I can, but I suggest you try it.
You try it.
You
will
try
see,
it, but on unimportant files.
Right. Just create some directories, subdirectories, just put some files and then just try out these things, have fun. If he shows it in the terminal, you will also see a couple of examples. That's it. Basically, you will forget. You have to try it. But try it on unimportant file, yes, Eddie has said. Create some directory XYZ, then create some subdirectories under it. Look at the commands, go to cd, make dir, do an ls or every step to see what is there.
Sir, sir, can we move one file to other directory and rename that file in just one command?
No, what's the question? This is this.
Yes, sir. Sir, can we move one file to one directory to other directory and rename the file in just one command?
That is it. Move the file to this directory
and rename it using only
No,
one command.
anything again. Okay, you can do it. Move file, directory slash the new name that you want to give.
Okay, sir.
Each of those files and directories can be a full path. It's not necessarily just a.txt. It can be /user /something /a.txt. So it'll just go there.
Okay.
But you need to have permission there to create that.
Yeah. So I assume that you have permission, so you can do these things. Likewise, you can copy file.
So means in file 1 we have to write the path of file 1, right?
It may be either a relative name or an absolute name, whatever.
So means where will it know where to search the file? Like we have to give the whole path, right? Which file we want to copy and
No.
which.
File search is not a problem. If you have a relative name, for example, if you consider this, you will look at this shell will look at the subdirectory this, then subdirectory, 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 and then it will locate this file.
So means we cannot just write myprog.c, right?
If you are in the current directory, if myprog.c is in your current directory, you can do it. You can also access it as myprog.c. Or you can give a fully qualified path name starting from /.
Okay, sir.
Okay.
Unlike executable files, for these copies and so on, it will not look up the path variable. You have to tell where it is. So if you don't tell anything, then it's assumed that it must be in the local directory, current directory. Otherwise, if you say .. myprog.txt, .. means take my to the parent directory, look for myprog.txt there. If you say /user /home /bin /something, then it goes the complete path you give. You have to mention the path.
No search path for it, yes. Unlike executable files, these regular files do not have any search path. Okay.
Sir, when we execute the first command on this page, like copy cp file 1, file 2, right? Then are the contents copied or like is the new file created in the second directory?
It's a new copy. File 1 will stay, file 2 will also stay, and there will be identical copies.
And like the angular bracket file 1 is a file location.
Angular bracket is just forget that angular bracket. So this is what is called typically.
Like copying one file location to another location, or like exactly what will this command do? I am unable to understand.
This bracket in computer science we often use this bracket. This is Backus Node form, BNF. So this is the entire thing is standing for some file.
So this less than greater than is not part of the command. You will say cp a.txt b.txt. So a.txt must exist. What it does is creates another file called b.txt with the content exactly same as a.txt.
And sir, where is that file created in the same directory?
If you don't say anything on the local directory.
Okay.
But if I say cp a.txt /user /include /b.txt, then a.txt will stay here. A copy of that will get made in /user /include / in that directory. A file called b.txt will appear.
Okay.
/user /include you will not be able to change unless you are root. But anyway, you get the idea. For each of those files, including the bracket is, as I said, this is just a standard way, get used to it, of specifying in computer science that bracket something means that is the entire thing you have to replace with something. Whereas CP is no bracket, that means CP is CP. You have to type C, type P. Bracket file 1 means this entire thing you have to replace with something because it can take many different things like your file name. A.txt, myprog.txt, b.c, whatever. Okay. Now those file names you specify as full paths. If you don't specify anything, it is the current directory. Otherwise, if you want it to be copied to some other directory, you specify the path to that directory.
Sir, if the file type do not match, suppose file 1 is txt and file 2 is dot something.
Doesn't
PDF.
matter, it's just a name. So if you have copied a file.txt to myfile.c, it's your problem. We are not talking about programming languages, nothing. If you have a file with the English paragraph in it, story in it, and then you copy it to myfile.c and you try to compile it with C compiler, that's your problem. This is just going to copy the file, that's it. In Windows also I can rename a file anything, right? It does not stop me. So there is nothing called file types or anything here. CP will just byte by byte copy this file into the destination file that you have put. Create that file, the destination file, and then copy byte by byte from here to there. That's it. It does not look at whether it's a text file or binary file or whatever. It doesn't matter to it at all. Is that clear?
Yes, sir.
Sir, if file 2 exists, it will copy, and if file 2 does not exist, it will create. Is it how it works, or?
No.
Yes, if your file, sorry,
if
go ahead.
it exists, then copy will fail. Or maybe
Copy will be overwritten. CP file 1, file 2. If file 2 exists, it will be overwritten.
Not necessarily overwriting. Possibly this if you are doing it in -i mode, interactive mode.
Then it will ask you for the whether you want to
whether you are trying to overwrite it, yes or no. If you say no,
let us
nothing
not
will
get into
happen.
-i. By default, it will overwrite.
Yeah.
I think,
Otherwise, it will be
Ah.
Otherwise, it will overwrite. Yes.
Okay.
And this is an important command, word count. So here I assume that this file 1, file 2, file 3, these are all text files. So how many characters are there, how many words are there, and how many lines are there? And if you have multiple things here, then the sum of these counts, sums of these counts are output by this WC. WC is essentially an abbreviation of word count. Okay. Sometimes are useful. Sometimes this command is useful. Okay. Okay, so these are some view modes. Okay. Of course, you can use an editor to view a text file. Or if you're in a shell, you can simply say cat text file. Cat is an abbreviation of concatenation. Concatenation comes from the fact that if you have file 1, file 2, file 3, one by one, they will be printed to std out. Okay. So for seeing the file completely, you can use this cat. Head prints the first few lines, usually 10 lines, but you can say head -20 to see 20 first 20 lines. Likewise for tail, the last few lines. By default it is 10, but you can say tail -25 text file. So it will give you print the last 25 lines. Okay. And there is utility less. I would suggest use less instead of more. So more was the original Unix utility, and this less is a much more, I would say, comfortable or sophisticated version of more. So this less command you can use for a page-by-page display. But once you go to less, there should be a way out, okay, because it blocks your screen. So you know this. If you want to get out of that viewer, just type Q. It will come out. Okay. And then one line up, one page down, half page up, half page down, go to first page, last page, things like that. Okay. You can also search for patterns in less, but not in more. Okay.
Sir?
Yeah.
Sir, what is the difference between less and more?
They are both page-by-page viewers. Okay. More was the original Unix command. Okay. It's not so capable. Less was something like the GNU version of more. Okay. And this is again a page-by-page viewer, but it is much more powerful than more. More works exactly the way as it's supposed to do in the original Unix specification. Less does little bit more than more. Okay. Okay. So you just type less some file name, text file name, and see what happens. Okay. And the only thing is that once you type this, your window will be blocked until the viewer goes. So just type Q. Where will you go? Okay. Try it out. Then you will understand what it is doing. Okay.
Sir,
Yeah.
sir, in the head command, you have written first few lines of text file.
Yeah, few is by default 10 in my system.
Okay, sir. So, sir, it varies from system to system.
I have not, I would say, read any Unix specification regarding that. Maybe 10 is the default. I am not very much sure.
Okay, sir.
Okay.
Sir?
Yeah.
Sir, cat command prints the contents in the text file in the shell.
Yeah.
Sir, how to open the text file in some editor, default editor?
Whatever editor you want, you will say gedit text file. Gedit.
Okay, sir. Okay, sir.
Or KAT, there is some Emacs text editor. There are many text editors. And if you are really, if you really want some kind of adventure, you can open the VI editor. But be very careful. If you open something with the VI editor, you should know how to come out. That's not so easy.
Okay, sir.
So right now, just use any graphical editor you have. If you are not used to it, use a plain gedit. It'll open a window for you with a normal window with normal drop-down menus and work on that.
Okay, sir.
Okay.
Sir, is VI editor a special application or is it within the console?
If you don't know it, forget about VI, don't use VI. Okay. First learn the remaining things, then you get into VI.
Yeah.
It's just a text editor, but you have to know the commands, otherwise you will be just stuck there.
Yeah, you even cannot come out.
Yeah, so forget about VI.
Okay. And then this is another thing, redirection. Possibly when you write C programs, you have come across these three things: std in, std out, and stdr. Have you? I don't know. I'm not sure.
I don't think in TIL algorithms they would have come across this. In TIL algorithm, there is no need to have write directly to 0, 1, 2.
But 0, 1, 2 they also do not need for algorithms.
Right, that's what I'm saying.
Oh, okay. Yeah.
So they will not. So the terms std in, std out probably will not be known to the class as a whole.
Yeah.
You can just explain what less than greater than does. That's it. No need to bring in std.
Actually, std is. I mean, this is used for reading. Std out. Your normal printfs will print things to std out. And if you want to print some error messages, you can do something like fprintf std error. So these error messages will also be written to your terminal, wherever you are running that thing. Okay. But there is a way you can separate this std out thing and stdr thing. Okay. Both are redirected to your terminal. Okay, but you can separate them. Okay. Now this less than and greater than, these are not those things. These are the standard, I would say, the BNF, Backus-Naur form kind of specification, but this less than and this greater than are not like that. So these are redirection operators. Okay. So whenever I say command, some command, maybe your ./error out, less than file, it essentially redirects this executables std into the given file, which means that instead of you supplying n equal to something, would you like to continue, yes or no, supply yes or no, instead of you typing the things manually, these commands or whatever you are supposed to input, they will be simply read from this file. Okay. So for example, let's say you enter a point, coordinates x and y, then you maybe you do two things. Okay, maybe how distant from the origin that point is, and some other thing. So you give another option, 1 for this distance, 2 for some other thing, and then you will quit. So you write x and y, whatever values you want to supply, and 1 or 2, whatever, in a file, and simply say ./a.out less than that file name. Okay. What will happen? You now do not have to type x, y, and the option 1 or 2. It will be simply read one by one from the file. Is that clear?
Yes.
Okay, good. Likewise, when you run something, the outputs will come to your screen. Okay. If you want that your output will not come to the screen, but will be stored in a file, use this other thing, greater than file. It redirects the comments std out to the given file. And if you want to redirect the std error to the given file, just say 2 greater than. 2 stands for this. So this stands for 0, this stands for 1, this stands for 2. Why? It will be clear, I think, in your OS lab course. Okay, this is a file descriptor 0, 1, 2. So 2 will go to file. And if you want this std out to go to out file and std air to go to air file, you can do something like this. Okay, greater than is just 1 greater than. Okay. Okay. And if you, instead of overwriting this file, if you want to append to it, so instead of 1 less than, instead of 1 greater than, you use double greater than. Okay, if you want to append. Otherwise, simple greater than always overwrites existing files, provided it does exist.
Sir?
Yeah.
Sir, these commands would run for only C++ or for all languages?
Why C++?
Sir, means std out, std in are official.
Oh, I see. Okay, std out, std in, stdr are C or C++ things. But when I am talking about these comments need not be your ./a.out. There may be ls-l. There may be word count, wc. Okay. Those things you can also do. And this is the convention. Because your Unix shell is written to follow this convention, std in, std out, and std error. Okay. If you write in any other language and follow this kind of thing, this will do whatever I say. It need not be error out. It may be a built-in command. It may be a command obtained by writing a script or by compiling anything other than C or C++. That's possible.
So anything for the less than thing, it is anything that requires you to give an input from the keyboard. So if you are supposed to give some input from the keyboard, instead of doing that, you will type whatever input you are giving in the file itself. You will read from the file. It can be anything. So suppose you are typing in a 5x5 matrix, that can be a C program, C++, Java, whatever. You don't have to do 25 type, time program. You have just type it once in a file in the same order and do less than, it will read the 25 integers one by one in your program. By less than, only thing you are doing, don't read from the keyboard, read from the file. You must provide the same input in the file in the same order. But the command can be anything that requires something to be read from the keyboard.
Sir, will it read the entire file or will it read something like
that? Whatever, think of your C program. First of all, let us not go anywhere beyond C program. So that's something you can relate to. You have done programs in those C, C++. Okay. So if you are doing 10 scanfs for 10 integers, so your program just requires 10 integers. File, if you type 100 integers for whatever reason, it's not going to read the remaining 90. It's not what is in the file, it is what the program wants to read. It will read first integer, first one in the file, second integer, second one in the file, third integer, third one in the file. After 10, the program has everything it requires, it runs. The file is just there. Normally, you will not put more than what is needed in the file if you want to use the less than. But all these things, I think now you should try it out. You know, every question that you are asking, they are good questions. But what will happen if I do this? All those what will happen? Can I do this? All those questions, actually, you should first, as I said, as we both said, like basically create files which are like, unimportant files. Do it on them, practice, see, try to explain based on the thing here. For every of these commands, you can just search in the Google. Then if you think that you don't understand, then you come back and ask, because you will not. So we are kind of providing you all the commands, relevant commands with the basic description in one set. But you cannot learn that only in the class. Okay, so ask the questions, but everything, please go back and try it yourself also.
Yeah. Most of the things will not bite you.
Create your own files. Even if something happens to them, what happens? Nothing. I think we need to wrap this up now quickly.
Yeah, I think it's
like long
this
time.
thing is another thing. So this command one is writing something to std out. And if you want that std out to go directly to the std in of command 2, you use pipe. Okay. So for example, ls minus l, this will give a long listing of the current directory. If you pipe it to WC, so WC will essentially count how many words, characters, and lines are there. Okay. And you concatenate this, whatever it outputs, that will go to less. This is same as writing less myproc.txt. Okay. Okay, so try these things out. And I think this thing you can just read where a comment is there. So there are certain things called which, where is, and what is. So we will see some information and something about users and systems. So uname minus a will give the entire, information about the system, who will tell you which users are logged in currently in your system. And W will give not only this thing, but also what they are doing. Okay. Okay, so that's about it. So there are many other.
Just one concluding thing. So don't worry. It's not that you will need. We are teaching this to you because you will need all this in your next assignment. Okay. But if you are starting to work with Linux, these are the commands you should get acquainted with. As we have told in the first class also, in this lab, if you just work oriented towards the assignment, that assignment requires me to do this and I will do only that, then you will not learn really. Okay, you may get marks, but you will not learn. So practice many of these things as you go on. It's not that you have to do it just for this assignment or anything like that. But you will need this to do if you want to keep on working with. If you have to keep on working with Linux. And there's a lot more commands that you will come to know after that. So try them out, see them, try them out. There's enough help on the internet also. But again, if you get stuck, you see something that you cannot explain. I did this, but this happened. I don't know why. Just send us a mail. Okay? Send your TS a mail, first of all. Otherwise, send us a mail. Okay, Eddie, I think we can go to make, I think now.
Yeah, so it's already 1 hour. Okay,
that's
so
what I'm saying.
Yeah, so I will start make, but maybe I just take a small break. But this will take some time. But anyway, please give me some time. Okay, I will come back.
Yeah, so I'm still here. So if you have any questions on the commands and all, right now we can use those. But again, as I said, you should first exercise them a lot. These are some things you work with the Linux system, you will do every day, basically. CD, make D, this, that. Just like in Windows, you do copy and paste, cut and paste. create directories, create files, text files, these files, open files. Same things, the corresponding commands in Linux. There are also graphical ways of doing it. But as Eddie said, sometimes we'll see later on that we want to do a bunch of things together. I want to find all files with a certain name from one directory and copy them into some other directory. So then you don't have to do it one by one searching for these things. You can write scripts and run them together. And you will use commands like this cd, cp, all those things.
Sir?
Yes, Polo.
Sir, right now I'm logged into Windows. So is there any something hands-on which we will be doing? So I should leave
Today?
and log into Linux.
Today, no. Today there is nothing going to be hands-on. No.
Okay, sir.
As I said, in an online class like this, we'll not be doing anything hands-on. We'll give you an assignment today, which you will do for the next 2 weeks. And you'll have to do it on Linux, of course.
Sir?
Yes.
Sir, the requirement is Linux terminal or else Linux OS?
Any Linux terminal right now, where all these commands we are saying runs, is fine.
Okay, sir. Thank you.
Okay. But you have a problem installing Linux right now?
Like I didn't try that yet, sir. Like I'm in confusion between whether to install dual boot or else virtual machine.
Okay. You should actually do a virtual machine right now. That is fine. For this course, it will be okay. But eventually, as a computer science student, you probably will need a dual boot laptop. Virtual machine is just slow because it's running on time, it consumes a lot of resource. When you get to your third year, for example, your OS lab, network lab, they will all run on Linux.
Can you use WSL?
You can, but they are all basically, as I said, they're emulating Linux on top of something. So again, you use whatever for this course, this lab, whatever makes you run, allows you to run basic Linux commands, and those commands that we have mentioned, make, gprof, and all those things is fine. Shell scripts and so on is fine. But all I'm saying is that eventually, almost all students that I've ever known in CS here ends up with a dual boot laptop. Third year, you will have labs which you must have Linux. So again, work with whatever you have, but if you are in campus, take seniors help or something. Installing is easy, but as I said, like it's good to have somebody who has done it kind of guide you.
Okay, I am back again. So now let us make it. Okay, so this is the second part of today's class. Let me 1 second go to presentation mode. Yeah. So why? So I will give you a brief description of why we need to make at all. So as you told in the very first class, that all our software projects are designed as modules, and compiling and linking all the modules gives you the final product or products, which may be one or more applications or one or more libraries. Okay. And there will be hundreds of modules, each consisting of maybe tens to thousands of files. So compiling everything is usually very time consuming. Okay. And if you make a slight change in a module, then possibly it is not needed that you compile the entire thing again. Okay. Because not all modules are dependent on one another. So if you make some change, Okay, only that module and other affected modules need to be recompiled. Okay, so we'll soon see an example, a toy example, of course, but never think about toy examples. These are all applicable to, or I would say they are designed, these utilities are designed to handle large software projects. Okay, so this process is called software building. Okay, only that module and other affected modules need to be recompiled. So how do you do that? Okay, so Meg is a utility that helps you achieve that. Okay, it essentially automates this building process, but then you have to give instructions to this utility what is meant by dependency of modules on one another. Okay, so once again, let us come back to our library example. Suppose that you want to build the static library libstack.a. Okay, what are the files? You have some header files, some C files. Okay, so these are the following 3 steps. Okay, these are the 3 steps that you should follow. Okay, first, generate an object called stack.o by compiling the stack.c with the -c option. Then you compile q.c with the -c option to generate a module called q.o, or to generate an object called q.o. And then you run the archive command to generate this libstack.a from the individual object files stack.o and q.o. Okay, so these 3 are the commands you should execute, okay, for building this. So this is a small thing, toy thing, so there are just 3 commands. But anyway, so you can write these 3 commands in a so-called shell script and execute that shell script to get the final product, which in this case is this static library libstack.a. Okay, but this is a small example. This is perhaps fine, but as I mentioned, you may be compiling millions of lines of code divided into hundreds or thousands of modules. So yeah, so if the source consists of thousands of files, compiling all of this is a slow process. And not all modules need recompilation after every change. So if one makes a small or large change in only q.c or q.h, okay, there is no need to recompile stack.c. Okay, so that is the important thing. Okay, if you make a small change in q.c or q.h, the only thing that is affected is this q.o. Stack.o does not need to be recompiled. Okay, and this make utility helps you in this selective recompilation process. And of course, you have to tell how to do it. Okay, so but before looking at this make utility, let us look at this so-called dependence graph or tree. Okay, so your final thing is libstack.a. If you look at this this thing, libstack.a depends on stack o and q.o only. Okay, so you first have the stack o and q.o ready before you go to generate libstack.a using the AR command. Now, on what things does the stack.o depend? First of all, the stack.c. Okay. Also, whatever is written in that stack.c, hash include stack.h, hash include deps.h. So these things are also needed. Okay. So if any one of these three things changes, you need to recompile stack.o. Likewise, q.h, deps.h, q.c, these 3 files are dependencies of q.o. If any of these 3 things changes, you need to recompile q.o. Okay. So if this thing changes, then you need to recompile this and this, or generate this and this, subsequently this. Okay. But if only this thing changes, you only need to recompile q.c to get q.o, and then rerun this archive command to generate this static library. Okay. So this kind of dependency is what you specify in a Makefile. Okay. So as I mentioned in Word, libstack.a depends on the object files. Stack.o can be generated by compiling stack.c with the -c option. And what happens, Make actually knows how to generate stack.o with stack.c because it knows the -c option, so it can generate that thing. But it does not know, this is not obvious to the utility, that the stack.c or stack.o also depends on stack.h and defs.h. Okay, so you have to mention those things. Okay. Okay, so likewise q.o can be generated with this -c option. But so Make knows that thing, but it does not know that the compilation additionally requires the header files defs.h and q.h. Okay, so how do you instruct Make to see or understand this dependency graph? This is not exactly a tree, right? Defs.h is directed to both stack.o and q.o. Okay, but this should be an acyclic graph. Its requirements cannot be circular, cyclic. Okay, so its dependency and compilation instructions are written in a file. Okay, and the three common files that they are searched are this. First, the Make utility will search for this file, GNU Makefile. If it is not there, it will search for small Makefile. If that is still not there, it will look at this Makefile with M capitalized. Okay, M in uppercase. So if neither of these files is found, of course you cannot run Make. But if you have Makefile in another name, like my Makefile, you can always say Make -f Makefile. So now this will be your Makefile. Okay, because you are specifying explicitly -f this. Okay. And you simply run the utility as Make without any argument. What will happen, I will tell a little later. Or you specify a target that you want to build. Okay. So this Makefile consists of several things, but the most important thing is a set of rules. Okay, and each rule is of the form target name, the list of dependencies, followed by how you generate this target name given this list of dependencies. So command 1, command 2, command 3, and there are certain things in order. Each line of this command must start with a tab. Never forget this. This is basically a tab. Okay. A line not starting with a tab ends the rule. Okay. So you say target name, colon list of different tab something, tab something, tab something, and then you have a new line or something not starting with tab. That essentially indicates that this rule is over. Okay. The target may be the name of a file. Okay. This target name may be the name of a file like libstack.a or stack.o, q.o, or it may be just a symbolic name, okay, which is not associated with any file. So such targets are called phony targets. So these are file name targets, these are phony targets. Okay, we will see examples soon. Okay. Okay, so dependency list may be empty. Okay, this may be empty. But in that case, what does it mean? That either this target name does not depend on anything, or there are some default dependencies that Make already knows. Okay. For example, Make knows stack.o must depend on stack.c. You do not have to specify it explicitly. Okay. And likewise, absence commands is also allowed. Okay, in rules. And what does it mean? First possibility is that this is just setting the dependencies. You do not need to execute any command against that thing. Okay, it's just setting dependencies. And this also means that make knows a predefined set of rules to build that target. Okay. Okay, so let us see examples. Otherwise, things will not be clear. Okay. Okay. So this is a general rule. So we have a list of dependencies, which are files or other target names. Okay. So when this target name is wanted to be made, it sees whether each of these dependencies is in the most updated form. Okay. If so, if not, it will build those dependencies first, and then it will build this target name thing by executing command 1, command 2, command 3, blah, blah, blah. Okay. And how does make know that things are updated or up to date? So it uses timestamps to determine which parts of the project need to be recompiled. Okay. Then the commands are executed if one or more dependency files is or are modified after the target was last built. Okay. If any of the dependencies are more recent than the timestamp of the target, then this will be built. Okay. But only exception is that phony targets are not associated with any file name. So there is no question of having a timestamp on some names like all, library, clean. Okay. They are always built. Okay. So now let us write the make file for our stack library. Okay. So you say that this is a phony name. You are not building any file of that name. Okay, so this is a phony target library. It depends on stack.o, q.o. And the command that you should execute for building this target is arrcs this.a stack.o, q.o. Okay. Of course, you could have given it a file name target, which is this name, libstack.a. You could have given it that name also, but I am just explaining phony targets. So I have given it a symbolic name library. So no timestamp can be associated with this library because there is no file of that name. Okay. And stack.o depends on devs.h, stack.h. q.o depends on devs.h and q.h. You do not have to say stack.o depends on stack.c. This is obvious to the make utility. Okay. And also you do not have to tell how to build this stack.o because make already knows it has to compile stack.c with the -c flag to generate stack.o from stack.c. Okay, so in words, this is like this. Library is a phony target that depends on stack.o and q.o, and that build involves invoking the ar command. Stack.o depends on devs.h, stack.h, q.o. So this stack.o and q.o, these are file name targets. These are not phony. They depend on devs.h and q.h. Okay. What make already knows, that is, you do not need to specify this explicitly, is that stack.o also depends on stack.c, q.o also depends on q.c. There is no need to specify these dependencies. So I do not write stack.c here, although if you write it, this is not a harm. Okay. Moreover, make also knows that stack.o can be obtained from stack.c and q.o from q.c by invoking GCC with the -c option. Okay. So you do not have to write any explicit, I would say, command below this stack.o. Okay.
Sir, why we are also writing that AR command?
First of all, this is a phony target. Library has nothing, no, I would say. It's not a file name, right? How does make know? This is one thing. And then you can say, if you just change it to libstack.a and you just say it is stack.o, q.o, I didn't try it out. If make knows that it is a static library and you say the dependencies, you have to, it may automatically do it, but I am not very sure because I never tried this. You may try it out. If you just give it the file name target libstack.a and simply say this, whether I would say make knows how to convert those targets to this archive. I doubt, possibly not, but it also
I don't think so. I think you have to specify this thing.
Yeah.
This is a phony target. You have to specify what the command, what do you want to do with
For
it.
phony target, you always have to, but if this is the target name is libstack.a, then whether
So you are saying libstack.a colon stack.o.
Yes, yes. In that case, does make no, you have to experiment. I have no ready-made answer. But library, of course, you have to specify something because it's a phony target.
I think on the other side is, I think that will not work also because you have to specify the flags for AR. I'm not aware of any environment variable that you can set to specify the flags automatically.
Yeah. Possibly Meg does not know this. Yeah. Possibly. That is also my initial reaction, but frankly speaking, I didn't try it.
Okay.
Yeah. So likewise, it knows GCC minus C, but if you want to specify some additional flags, that Meg does not know. What additional compilation flags you need with GCC minus C. So you have to somewhere specify these things. Okay.
Excuse me, sir.
Yeah, tell.
Sir, like if we specify GCC in this stack.o, so will it compile only once or twice?
We will see. Let us see what it does. With a clear example, we will see. Oh, you mean you just write a command here?
Yes, sir.
Only once.
Like will make use.
What if you give explicit instructions? Of course, this will override the default behavior. It will not compile twice. But in absence of specific instructions here, it will follow the default rules.
Okay,
of course, you can write things here that will override the default behavior. Definitely. Yes.
Yes, sir.
Yes, yes. Okay, now I understood your question. Yeah. Okay. Now, so suppose you call make library. So library is a phony target, so it will always be rebuilt. Okay. But the dependencies are stack.o and q.o. But before invoking AR, make checks whether any or both of the dependencies stack.o and q.o needs to be rebuilt. And since this is a phony target, this AR will always be executed. Okay. But whether this stack.o and q.o needs a rebuild, that is dependent upon the dependencies of stack.o and q.o respectively. Okay, so the idea is this. So stack.o depends on stack.c. This is the default thing. It also depends on defs.h and stack.h. Okay. So what make will do, it will check this timestamp of stack.o. If that is more recent than the timestamps of all of these files, this, and this, okay, this means that the stack.o was built at some point of time, and after that you didn't change defs.h, stack.h, and stack.c. So there is no point of rebuilding stack.o. Okay. On the other hand, if it sees that one of these three files, or maybe two or three, all three, is or are more recently modified than the stack.o, then it will build stack.o from stack.c using GCC minus C. Okay. And the same thing will happen for q.o. Okay. The dependencies are test.h, q.h, and q.c. If they are older than q.o, it is not rebuilt. If one or more of this is or are newer than q.o, then it is rebuilt. And then it will invoke the AR command. Because it's a phony target, it will always be made. Okay. Okay. So any questions up to this point? So this is the basic thing. We will do whatever in the rest, we will do something additional things. So up to this point, is it clear?
Sir, in the previous slide that you wrote, that thing we need to write in a terminal or in some file.
That's what I told you. These things, right? I have to write in that makefile. GNU makefile or small makefile or uppercase M makefile. Or if you write in any other file, you can call make with make -f your new file name. This must reside in a makefile. These are not terminal things. But you invoke make from the terminal. Okay.
Sir, so then makefile is a file which we have to keep it in direct.
Yes, it's a text file.
Oh, okay, text file. All right.
So, which target to build? As you see in this example, there are 3 targets: library, stack.o, q.o, and suppose I have written it in this order. Okay. If you simply call make, it will always build the first target. The first one. So it will build library, not stack.o or q.o. And if in that process it wants to rebuild stack.o and q.o because these are dependencies, it will do so. So if you just run my make, it will make library. But you can individually make stack.o. So you can run it like make stack.o. That in that case, q.o will not be rebuilt because it's not a dependency. Library will also not be rebuilt. And if this is more, I would say, recent than this, and stack.c, it will not be rebuilt. We'll see examples. Okay. Okay. So default is, if you do not specify any target, it is the first rule. Okay. For example, if library is the first rule, it is built. Okay. Otherwise, you can specify a specific target name like make stack.o or make q.o. Okay.
So don't we need to mention the make file? Like, can't there be multiple make files?
No, that's what I mentioned. If there are multiple makefiles, if it is GNU makefile, that has the highest preference. If it is not there, it will search for small makefile. If it is there, it will be taken as the makefile. If it is also not there, then it will look at the capital makefile.
Okay, sir. So if stack.o, okay, it will check where stack.o is in this order.
No. If it finds capital GNU makefile, it will try to find stack.o there. If it is not there, it will issue some warning message or error message and it will quit. It will not search for stack.o in all possible makefiles. The first one it gets, it will be happy with that. Okay, so if you have all the 3 makefiles, GNU makefiles, lowercase makefile, uppercase makefile, okay, then it will read only from GNU makefile, not from multiple files.
And we have a way of specifying your makefile that will come later, I think.
And -f, you can
-f, yeah, use -f to give basically specify if you want that it to go to one particular makefile. The default is all those prior orders that AD has just mentioned. But if you want to rename your makefile to something, just to make -f that one stack.o.
Okay, sir.
Yeah, make -f your file name and then stack.o, whatever. Yeah.
Also,
okay.
Sir.
Yeah. Yeah.
Can we not build all the rules at once?
I would say usually no, but it depends actually. Let us wait a little bit. I will introduce some new rules. No, you cannot do that. Okay, and it's also not making any sense. We will see. We will see why.
Okay, sir.
Okay, let's wait a little bit. Variables can be set using the, now there is something called a recursive assignment and some non-recursive assignment. Maybe if we have time, we will look at it. Okay, a variable. So this, you can set some variables there. Okay. And you can set var equal to something or var colon equal to something. There is a subtle difference between these two things. Okay. But in the examples that follow, there is no difference. We can do any of the two things. Okay. And if you want the value of this variable, you write $var. Var is within either a pair of parentheses or a pair of braces, curly brackets. Okay. And in addition to these variables that you declare, make has a set of default variables. So it's a long list, but here we will use a few things. Shell specifies which shell to use for running the commands. So you have a target, colon, dependencies, and then command 1, command 2, command 3, command 4, and so on, right? Now, each of these commands requires a shell for running. Okay. So don't confuse shell with a terminal. A terminal is a graphic introduction window. And whatever is running there is the shell. The shell can also run silently without any terminal or that thing or that thing. Okay. Shell is just a command interpreter. So you invoke that shell and tell it which command you want to execute. It will do it. It does not require any window. Okay, for doing that. And shell specifies which shell to use for running each command. CC specifies the C compiler that you want to use. The default is GCC, but if you have some other compiler like the Intel CC compiler, ICC installed in your machine, you can specify by CC, I mean ICC, not GCC. Okay. Also, the shell default is bin share sh. Okay. And C flags, this is also useful, stands for the additional compilation flags that you want to use in tandem with GCC -C. Okay. So here is an example. So you say, of course, this is the default thing. Possibly you do not need to do it. If you want to give some other shell like TCSH, possibly you mentioned. CC is GCC. And the additional C flags that you want during your compilation process is the optimization flag at level 2, the debugger flag G, and I dot. Okay, this is the include flag, include directory flag. Okay. Also, you can give other things like AR is AR. And you can also call libname to be this thing and object files to be this thing. Okay. Then you say that your library depends on $object files. That is expanded to stack.o space q.o. Okay. $AR expands to AR, RCS, then $library name, which is libstack.o, and object files are stack.o, q.o. And then you say that this object files, that is stack.o and q.o, they both depend on deps.h. In addition, stack.o depends on stack.h and q.o depends on q.h. So this way also you can specify the old make instructions. And this essentially, but anywhere you do not need to call these C flags. Okay. because this is a default variable, and therefore whenever make compiles stack.c to generate stack.o using the -c option, it will automatically, I would say, supply these extra options that you specify using cflags. Okay, you don't have to write that command explicitly. Although if you do so, that will override the default behavior. But by specifying cflags, you can tell make that I want these additional flags for compilation of .c files to .o files. Okay. Yeah, any question?
So this text we have to write inside a make file.
Yes.
Okay. Yes.
Yeah. Okay, so just let us look at an example. Maybe this example itself. Okay, so this is what is the content of makefile or GNU makefile, whatever. Okay, and then you simply call make. Library is the, look here, library is the first target. Okay, not this one, or this one. Okay, so this will be built. You can additionally specify make library, that has the same effect. Okay, so then you see that in addition to -c and -o stack.o or q.o, it additionally uses these flags -o2, -g, -i dot, and it compiles this. Eventually, it will combine this stack.o and q.o to this library using the AR command. Okay. Now, if I do not do anything on any of the source files and once again call make, you see that this stack.o and q.o are not again rebuilt. Why? Because they are more recent than all the dependencies. So if I once again say make, these are not rebuilt. However, because this first target is a phony target, whatever commands are there, it will be executed once more. These phony targets are always built. Okay. Now this is another unique command. So touch essentially changes the timestamp of any file or files to the current time. So if you touch definitions.h, what happens? It acquires a new timestamp. Okay. Then again, if you say make, you know, stack.o depends on defs.h, so it will be rebuilt. q.o also depends upon defs.h, so it will be rebuilt. And once again, this archive command is executed. Whereas if you touch only q.c, on which stack.o does not depend, and then you say make, only this q.o is rebuilt, stack.o is not rebuilt, and then once again this archive command is executed. Okay. So these essentially illustrates the selective recompilation process. On a very small and toy example, but I hope you understand this, you follow this.
Sir, can you show the previous slide once? Okay, sir, thank you. Okay, so you understand this selective recompilation, right? If nothing changes, then there is no point making this file name target stack.o and q.o. But because library is a phony target, this is always executed. And then if you change some of the files by touching or by editing or whatever way, and all the things that depend on it will have to be rebuilt. And if you touch or edit, okay, only some file, then only the targets that require rebuilding are rebuilt, and so on. So is the process clear?
how make works?
Yes, sir.
Good. Okay, I think this is the basic thing, and whatever remains. Oh, okay. There are some other rules. Okay. Yeah. As we mentioned in the last class, the final products, in this case, libstack.a and the header files, need to be installed in the systems area. Okay. But you are a general user. Okay. And you usually do not have permissions to write to these systems directories. So you often write a rule called install. Okay. And under that install, I would say target, you specify which files to copy and things like that. Okay. So here our install rule goes like this. First of all, it depends on library. So this is also a funny target, install. There is no file called install. Okay. It depends, this funny target depends on another funny target library. Okay. Library in terms build depends upon stack.o, q.o. Okay. And library directory is this. Just as an example, include directory is this and include subdirectory is this. Okay. And what it will do, it will simply copy this library name. Library name was libstack.a to library directory, which is user local lib. Okay. Then it will try to create a new directory called include subdirectory, which is what? Include directories user include /stack. Okay. And it will copy deps.h, stack.h, q.h to that subdirectory, and also just stack.h to the include directory. Now, if you do this multiple times, every time you want to do it, it will try to create this directory. But if it is already present, mkdir will fail. Okay. So by using minus, you are saying that if you are unable to create this directory, ignore that error and proceed. Without this minus option, this building this rule will basically fail because mkdir fails. By specifying minus, you are asking make to ignore this error, if any, happening from this statement. Okay. Okay. Okay, so it's a dash before a command line, the command detects make to ignore errors. If the directory already exists, this fails, but make moves forward, ignoring this error. And so let us see how I can make install. First of all, I have to write in the systems directory. So I have to run it as a super user. So I say as a super user, do make install. It will ask for my password. And then it depends on library. And I assume that stack.o and q.o are up to date. So it will simply archive it to this and then copy this thing to the local lib. mkdir this cannot create directory, file exists. But here you say because I have used minus there, it says error 1 ignored. And then you copy this to this and copy stack.h to user include. Any questions?
Sir, in the previous slide, sir, install is depending on library. Is it a phony?
No, I didn't write these things here. Library is this thing. This thing. In addition to these things, I have those additional lines.
Okay, yes, sir.
After this, I have written install colon whatever is written there, and maybe this variable definitions are given here. Okay. Okay. Yeah.
Sir, is there any other word like library?
No, many things you can give. A very popular word is all. ALL. Make all. And you can give any name.
Okay, sir.
Okay. And another thing is cleaning previous builds. Okay. So once again, somewhere near the beginning, I say RM is RM minus F. And then clean means in this context, you remove the object files. Okay. And once again, you should do it with minus, because if the files are not already present, then this will raise an error. So by writing minus, you are asking Make to ignore these errors. And even this is a distribution clean, then you also did remove the library name. So this clean, dist clean, these are not, I would say, keywords, but used by many software developers. Make clean, make dist clean. Okay, so these are kind of, I would say, terms that are used by the community or that have been used by the community for ages. Okay. So let's see what happens if you run make clean. Oh, okay. Anyway, it will simply remove anyway. This is not demonstrated. Okay. Yes. So what is the time? Actually, I didn't spend too much time on make. Okay, you tell before you go to some, I would say, peripheral topics. You tell if you have anything else to know at this point. If anything else unclear. No, everything is clear. Great. Okay, so shall I leave it to you? The difference between equal to and this. This is a recursive assignment. Maybe you just read it. Okay. And here, like your hash include things, you can write your makefile in pieces. Okay. And you say include file 1, file 2, file 3. Okay. For example, here, let's say start make files at this, defs and primitives.mk. So these are some file names you have given. And then you say include preamble.mk, $this. So these files will be substituted for this, and util*mk, whatever files in your directory exists. Assume that there are 4 matches, util1.mk, 2.mk, 3.mk, final.mk. Then whatever is written in those files will be included exactly as hash include does. Okay. These are all included, and then you proceed. Okay. Yeah, and this is the last topic as far as I remember. So recursive make is go recursively into subdirectories and make. Okay, so cd to each subdirectory and call make. Okay. Again, as I mentioned earlier, each line of command opens a new shell. So both cd and make must be in the same line. Okay, so let's see an example. So suppose I want to make both the libraries. So all go to static directory and make there. Do not write the two things in two different lines, because this line is executed using a shell, whatever you specify, bin sh or bash or tcsh, whatever. Okay, ksh, whatever. So this entire thing goes to one shell. And when that shell returns, once again, you are in the same directory as you were earlier. Likewise, you say cd shared make. In our case, this is make library. Okay. Likewise, install may be like this. Go to static directory and make install there. Go to shared directory and make install there. Likewise, clean can be something like this. Go to static directory, make clean there. Go to shared directory and make clean there.
Sir?
Yeah.
Sir, why does it open one cell every time a new command is in every new line?
Why I do not know. There may be a reason, but it does so. You need to know that it does so.
Okay. Fine.
So that means once this is executed, the old shell is no longer there. Okay, so the CD static thing is now lost. That is why you write whatever you want to do here in the same line. Okay. Why the designers went for that? It's a difficult question. I never thought about it. Okay, so this is the transcript. Make cd static semicolon make. Enter this directory, build it, and so on. Make shared install directory, entering directory, do this, shared living directory. Make clean means go to this, you clean. Clean involves rm-f stack.oq.o, do it, living directory, go to this, entering, remove stack.oq.o, living directory, $. Yeah, I think that's it. And one thing I never mentioned here. So whatever make is going to do, it actually echoes that. Okay. For example, in this all, it is doing this thing. So it echoes that. Okay. Likewise, in the subdirectory, it echoes whatever it is doing. Okay. And if you want to avoid this echoing, you can simply write at here. At cd static. Minus thing you have seen, right? Ignore errors. And if you write at here, you are essentially instructing make not to echo whatever you are doing. Okay. In other words, proceed silently. That kind of, I would say, directive.
So will we write at cd static and like?
Yes, yes. So that will no longer, I would say, echo this message. Okay, these things it will do anyway, because it's part of the building process, but this will not be echoed. Okay. Yeah, that's it. Okay. So I hope this idea is clear. Why Makefile and how you can write your own Makefiles suited to your software building process. Yes or no? Okay, no more questions. So I will hand over to AG then.
Okay, so if you can stop presenting.
Yeah, so I will now stop presenting. Yeah, stop presenting. Yeah, so I'm done. Okay, so you continue.
Yeah. Okay, so here comes your first assignment. And it involves GCC and Make. So you have learned a lot of new things on Make today. So you need to work on that, practice writing. Don't go to the assignment directly. Okay. So all those things that Eddie has taught you today, kind of write small files, test it out, make sure you understand. Okay. Make sure they are working and so on. Small things are always easier to debug if something goes wrong. Okay. By the way, can you see my screen? All of you?
Yes, sir.
Yes.
Yes.
So what you have to do is to build a dynamic library, build a static library, and build a exe. So there are 3 Makefiles. Okay, they're all going to be separate. Okay, there will be a dynamic library, Makefile for that, static library, a Makefile for that, and then a Makefile for the executable. Okay. But then we also want you to kind of get more practice And just writing the make files is going to be very small work and also boring. So you need to see that the entire thing is working. That would be good. So we want you to write a lot of C code of things that you know already, okay, that you have covered in your algorithms course and so on. So basically, the first dynamic library that you are going to do is going to be a library of some basic data structures. Just give me 1 second. So the first one is you are going to build a dynamic library here, okay, and this is going to have, so these are data types that you're going to declare, so that in my files I should be able to declare an L list L, and that will kind of make a single linked list, okay. And then so you have a linked list type. You can read the exact prototypes later on, okay, but just as an example, okay, if you want to search, so you pass a linked list, I pass a number to search, it's a linked list of integers, and you will return to me the node star, the node containing that number if it exists in the linked list. If it does not exist, null otherwise. So standard linked list functions of searching list, inserting at the beginning, deleting in the list, and you have to create a list. But then you have to think a little bit what this L list type should be. What are the things that you need to keep track of? Okay, is it just the head? Is something else? You need to think about it, what the type is. So you cannot change the prototype of these functions. So you cannot make one of these L list h as L list star h. Remember what we said in the first team, this kind of a library that you are giving to others to use. Okay, and you have already said that this is going to be prototypes. So you cannot just arbitrarily change the prototype now in your implementation. Okay. So it will be linked list. There is a stack. For everything there is a create stack or something which is just going to create that basic data structure that you want, initialize it and so on, and then do all these checks. Is empty, returns the top element. Okay, just look at these things. I think you will understand. So you have L stack, queue, and heap. Up to this, I'm not going through it, each of them. These are standard functions for queue also. You have to create queue, front queue, enqueue, dequeue, and so on. And heap also, there is a create heap, find mean, extract mean, and so on. Okay. So note that we are doing it with linked list, the stack, queue, and so on. The stack and queue we're doing with linked list, so there is no notion of a full linked list. So there is no function required for is full stack or is full queue or something. Okay. For heap, you are going to implement it with an array, and we have given you a maximum size also of 100 element. Okay, and you can create a heap, find mean, extract mean, insert heap, and so on. And then the structure, the other one that you're going to do is union find. Now we know that you have covered union find in your algorithms class. Am I right? Yes, no, please.
Yes, sir.
Yes. Yes.
Right. Okay. So you know, basically, just to recapitulate a little bit, it's a disjoint set data structure. That means it keeps a set of sets and there are no two single same elements basically. Okay, and the way it keeps it, each of those sets are kind of represented as a forest. It may have a single element, it may have this, there may be some more and so on. So each element has a distinct value in the entire thing. So the disjoint set of sets is kept as a disjoint forest, each of this creating all the elements in one set. So basically this is a data structure in this example which has 4 sets. Okay, and we have a parent pointer, and the operations that we have similar to the create, you have a make set operation which makes a set out of an element. Okay, if you recall union find a little bit. So actually let me come back to this I a little later on. You pass it an union find f. At the beginning basically it's going to be the union find structure. Just bear with me for 5 minutes, go through this and then we'll have an example. So I pass it an unified structure inside which I want to do the make set. I pass the value of the element that I want to include, and I pass a star I pointer to get back an index. Index to what? We will see. Just give me a second. Okay. So let's look at the example. I think then the other things will become clearer much more. So this is your union find data structure. Basically, the data structure is the entire thing. But when I make the create, sorry, just give me a second. When I do this create function call, create uf int n, okay, what you are doing is creating this array of pointers. Okay. From each of them, so if I have n elements, then at most you can have n sets. You cannot have more than that. So I may have less sets, that's okay, but I'm going to create an array of n pointers. Pointers to what? We'll see. Okay, and I will initialize them all to null initially because they are not pointing to anything initially. So that's what your create uf will call will be. Then when I make a make set call, so I've created that thing. I say make set that f, let's say the number 10, okay, in some variable, and I pass an ampersand I. Okay, what it will do is it will find the first free entry here. Okay, so the first one will be here. It will store the 10 here. In this case, it's storing the 34. Okay, so this one is the value that you store. Okay, and this one is in that disjoint forest thing, the parent pointer. Okay, so the effect of make set is to find the first non-empty index here, create this node, put the value there. You have just created the set, a new set, so it's the only element. Make this parent pointer null because that's the only element out there, and then return this index into this I here. And this is what the application will refer to later on. Is that clear? If you recall, so basically I'm creating a set with only the element 10 in it, and only the 10 element I'm basically saying I put the value 10 here and I make its parent pointer point to null because it's nothing. Okay. So that's my make set. Then you know there is a find operation in union find. What does find do? Normally it passes a value and then it gives me an identifier of the set that that value belongs to. The identifier typically can be anything. Let us take the value of the root element of that forest as the identifier. So identifier for all these elements will be the value stored here. Identifier for all the elements out here will be the value stored here, or the node, this particular node in this case. Okay. So what I will pass in this find def is not the actual value, but the index that I got back from the values. In my application that is using union find, I will do the make set that will return me the index for that value. I'll keep that. I'll remember that somewhere. Okay. I can have an array of things saying that one element is X, the other element is I. And then when I want to find operation on this element, I will not actually send the value because then I have to search for the entire thing again. Okay. I'll pass this index. So now what this will do is I suppose the tree has something more also, just so. And suppose I pass the index of this. Okay, so this is basically I'm passing where is this particular element stored. Okay. So then I have the parent pointer. From that I will follow the parent pointer till I hit a parent pointer that is null. That means that is the root of the tree. I will take the entire node and pass a pointer to that node back to this. Okay. So it passes the pointer to the root node. If I get the pointer to the root node, I can always get the value back. Okay. With me? Yes, no?
Yes, sir.
Okay.
Yes, sir.
And then union is the same thing. I'm going to pass two integers. the two indices of the two sets that I want to unite, the two values rather, their corresponding indices I pass. So it merges the set containing the elements pointed to by the ith and the jth pointers. Okay. And assume again that the indices corresponding elements are known to you when you call this function. So these are the ones that you have received when you created that element, makes it out of that element, makes it out of that element, and you have stored it somewhere in an application. Okay. So now what you do is basically the merging function, but you have to do something that is not there in the picture. If you recall, there are many things in merging in the union. So you want to merge, make the tree with the smaller nodes, number of nodes. So if this was one tree and this was one tree, what you want to do is to make its parent pointer point to this so that the level does not increase too much. This is a standard union operation with one particular heuristic. And if you recall, in find, you normally do path compression. Here you don't have to do path compression. It's simple. Okay. So take this example now. This has 3 sets. Okay. So very originally it has 8 elements. At the beginning, I basically did a make set of each of those 8 elements at some time. Each of them basically therefore point to 30. Each of them is pointing to one of the elements. Okay. And then the other ones are not used. I have initialized them to null, so they stay null. Okay. Now this kind of in the intermediate stage after I did some merge operations. So if 3 of them 34, 47, 9 are in the same set. Okay. So basically what I will see 34's parent pointer is null. So 34 is the root actually. So this is my 34. Okay. Then I go to 47. 47 is pointing to this 34. So 47 is pointing to this. Okay. And then I see 9. I see 9 is pointing to 47. So this is basically this tree out here. 9 pointing to 47, 47 pointing to 34. So this set is represented by this particular tree. Similarly, I see 19, 5, 11, 28. Okay. Out of this, 11 has the null thing. So 11 is the root. Okay. Then I see 19. 19 is who are pointing to 11. 19 is pointing to 11. 28 is pointing to 11. So these are simply the parent pointers. Okay. And then 5 I see is pointing to 19. So this set is represented by this tree. Okay. And then I have a singleton set 23. All right. So this is basically what is represented by this structure. So now if I do find, so let's say these are basically your index 0, 1, 2, okay, up to something, up to 7, okay, 3, this is 4, okay. So if I make a find on this structure F, if I make a call find F, okay, let's say 5, okay. So basically it will go to the 5th index 0, 1, 2, 3, 4. Okay, sorry, index 5 itself, not the 5th index, index 5 itself. So actually the 6th index. That will be the element that I'm referring to. So basically I have made a call to say find F47 actually, because each of them is pointing to exactly one element. Okay, so then I will just follow the parent pointer path. I see it is 34. So I will return the pointer to the entire root out there. Node out there. Okay. Same if I call find F3. So 3 is this one, that is 23. I'll just return itself basically. Okay. And then if I say union, let's say F, the set point 3, the elements containing 3 and 2, just suppose. Okay. So basically 3 is this one, 2 is this one. So I'm basically merging the sets containing 23 and 5. So basically I'm merging these two sets. Okay. Now this is not there in this picture. Somehow you have to remember also in this structure, for the root node only it will be relevant. What is the number of nodes in this tree? Okay, suppose I have that. Okay, say this I have, this one will be, okay, this is the one that I'm merging. So this has an additional field which is 4 and this has a field which is 1. I'll go to the root, I'll find the things. Okay, I'll see this one is higher than this. So I'll make this parent pointer now point to this. Okay, and I will update this with this plus whatever is here. So 4 plus 1, that is equal to 5. So this basically says now my tree has 5 elements and the tree that I got is basically this 23 here. Is this clear? Yes, no, please.
Sir, could you please scroll up a bit?
Scroll up. Okay, for previous page.
Yes, sir.
Okay.
Yes, sir. So the union of two nodes, we do not need to return anything.
No, because you see this structure. Yeah, this is the thing that we discussed. This structure is not changing. What is being changed is out here. Okay.
Yes, sir. Yes.
So the create graph basically this pointer is the one that is the important thing. That is the F structure basically. Lots of things are hanging from. And once you have, so only the make set is going to change something in here. Nobody else is going to change anything in here. Because in union find there is no delete operation.
Okay.
Okay.
So,
any other questions?
Can you once explain how are you finding the level of node in union find?
No, that's what I said, that here, for example, that field is not there. So think of there is one additional field with each of them. Okay, that is your node that we are talking about. Okay, so when you make set, you set the field to 1, which is because there is only one element in the set. Okay, now think of the very beginning. There are two make set things, two elements that you are trying to merge, each has one element. So you will decide basically if it is same, you can choose arbitrarily. So suppose you choose this one, say suppose there was another element out here, just suppose. Okay, something. Now suppose you decide that this will become my root, this also had 1. Okay, and this will become the child of this. Okay, so I'll make this pointer point to this when I do the make set, sorry, the union. And then I know this one has one element below it. This one already has one element below this. So 1 plus 1, I will update this count to 2. So at the root, I will always keep a count of how many elements are there in the subtree. So basically any nodes thing is going to tell me how many elements are there in the subtree below it. So I'll just look at this value for the two roots. The one with the smaller one, I will make the parent, sorry, the child of the other, make its parent pointer point to there. And since I'm now adding this entire tree, that root's value is going to change.
Yes, sir.
That is clear?
Yes, sir.
Okay. Any other questions?
Sir, the in the previous page for find set, we are using node PTR. Sir, that structure we are free to define according to us, right?
You have to define. See, yeah, so you can define it according to you. Actually, Eddie, are you there? Okay.
Yeah.
Okay, I don't need the node PTR, right? I need the int only because we are not going to use it anywhere.
Int also you can do, but yes.
No, because see, first of all, you can compare the pointers also because it's basically the same element.
Yeah, under the assumption this
but let us not expose it. Let us not expose it to the higher level thing. I think we can change this to int easily. Yeah. So you return the value instead of the node pointer.
So long as this int values are different.
It's a disjoint set.
No, disjoint set, but same element may appear multiple times in different sets. And anyway, in our application, this will not happen.
No, I see what you say, what you are saying. Okay, let's keep it. Let's keep it. So the answer to your question is, see, what are you going to do with this find thing? Basically, Again, so yeah, let us discuss and get back to you. Okay. So Eddie, the thing is that again we want to make it very generic. Then we have to expose the node pointers internal thing if somebody wants to get the value out of it. For again, for our purpose, it will not matter because you can directly compare the address only.
The node pointers are anyway accessible by those indices.
Node pointers?
Accessible by that if.
Right, but then you need to know the structure of the node pointer in the application if you want to get the value out.
No, we'll just
compare the name of the field and so on.
We'll just compare the pointers.
Right, that's what I'm saying. In our case, it is fine. But again, for a general thing where values may be required, our case, this is fine. Okay, let's keep it. So answer to your question, whoever asked, you have a type called node pointer. You will declare a variable called node pointer. So you will make two find calls. We'll do Kruskal's actually with it. Okay, you will get the node pointers back. You will just compare the node pointers because it's basically the same element that is there. The same nodes pointer that is being returned by both of them if they are in the same tree in Kruskal's and so on. Wait till we do the Kruskal thing. And then I think this will become. Okay. So you build a DLL. What you have to do is to for each of these things, for each of them have to be placed in the functions in a separate C file. And then for each of them, there must be a corresponding .h file. So you should know what to put in .h, what to put in .c. And we have told you, okay, basically you put all your preprocessor directives, okay, type defs, function prototypes in your .h, and the actual codes in the .c include the files. And then you have to do a little bit when you do the assignment, what to include when and so on and so forth. You don't want to include too many things unless it is needed. Okay, so think about that. That's one of the things that you want to do in the assignment. So general thing is in the .h file, we say that you should not have anything that will occupy any storage. Like any variable declaration actually should not come into this. Any function code should not come into this because the code when it runs will occupy storage. Okay, so you need not want to do that. So again, guideline is, as we have told earlier, any preprocessor directive can be there, type defs can be there, structure declarations, type defs, and so on. Function prototypes can be there. Okay, actually they should all be packed off into the thing. Your .c file should not have those basically, but the code should all be in the .c file. You will just include the appropriate .h files. So for the 4 of them, you have to write 4 .c files and corresponding 4 .h files, and then create a makefile to create a dynamic library out of them. Here is an example that you want to name your makefile something else because you have multiple makefiles. So you will use the -f option. Okay, and you have to use the clean and install all those things also. The rules for that was just discussed. Okay. Now we want to use this library in another library.
Or they can write in different subdirectories.
Which one?
This part 1 and part 2 may be into different subdirectories.
You can let them get used to -f also. Lots of time you have different makefiles also.
Yeah, that's okay.
Let be. Okay.
Or they can write a single makefile and.
No single makefile, please.
I have different rules.
No. I want them to write separate makefiles.
Okay. Let them do it. No, it's not.
Just this is like as if they're completely independently developed by somebody else.
No, this is not possible here because there are some technical issues also. Yes, you have to write 2 different makefiles.
Okay. Now we want to use them. So you have to build a static library for graph functions. Okay, and the graph functions we'll do is DFS, BFS, and MST using Kruskal's. And as we'll see, DFS, BFS code is very trivial. And Kruskal's is also very trivial once you have that union find data structure built. You just make find calls and so on. Make set for everything, find calls, compare them, and the same thing. If they're not the same, then equal. You know what Kruskal's algorithm does. Okay. So first thing that you need to know is this read graph function. So we are dealing with weighted undirected graphs in general. Okay. So read graph will take a file name So you will kind of input the kind of type the graph in a specific format in that file name inside that file. And in my application, I will make a call to read graph with the file name. Okay. And this will read the graph, create a graph structure. And the graph structure we want is an adjacency matrix. So you have to store n nodes. Okay. You decide how to create that two-dimensional n by n cross n adjacency matrix. This n will come from somewhere. We'll see. It's inside that file. Okay. So this is like creating the graph data structure, this adjacency matrix, and reading the corresponding weights and so on. Okay. We deal with only positive integer weights. That means if an edge is there, you put the weight of 10 or something. In that entry, you put 10. If an edge is not there, you can put a 0 out there. Okay. Because the valid weights are only positive integers. Now that you have the graph, I just want to pass the graph, do a DFS, print out, just print out the values, the order of the nodes in the DFS traversal. Okay. And to do that, you need a stack. You will use that stack data structure out there, the stack type. Then we want you to do BFS. Again, you know that BFS requires a queue type. So use that queue type. Call the functions of that to do enqueue, dequeue, create a queue. So kind of in your BFS code, okay, you will declare a queue. You will call a create on that first. Okay. And store the value in the queue. And then you will call enqueue, dequeue on that queue with the value that you have there. Basically call those functions. Right. And then you want to do Kruskal's, and you should print out Kruskal's output is a set of edges. As and when you select an edge into the spanning tree, you print it out in a single line, just like 2, 3 to indicate that edge 2, 3 is added, 1, 8 to indicate edge 1, 8 is added, and so on. And finally, you want to print out, let's say 127, the total weight of the spin band. So this is easy to keep a running sum of the count. Okay. And here is the format of the file. You can look at it later also, very simple. So the first line of your file will contain the number of nodes. It's 4 here, so 4. Second line will contain the number of edges. So there are 5 edges, so 5 edges. Okay. And then each line will contain information about one edge. So since the number of edges is 5, you have 5 lines to following it. And what does it say? If there are 4 nodes, my nodes will be numbered from 0, 1, 2, 3 up to n minus 1. Okay. So this will be 0, 1 saying there is an edge between 0 and 1. Remember, it's undirected with weight 31. There is an edge between 0 and 2 with weight 10, edge between 0 and 3 with weight 11, and so on. You can verify that the representation of this is this. So in your read graph function, you will first read these 4. That tells you what size of adjacency matrix to build. And then this tells you how many lines to follow. You read each line, 3 integers. First one tells you what is the row number. Second one tells you what is the column number. And then the weight out there. And it's undirected. So 0, 1, 1, 0, both will be 31. You have to put that. You know how to represent an undirected graph in this. Okay. And the BFS DFS, you know, BFS DFS does not require weights. So when you do BFS DFS, just ignore the weights. Think of the undirected graph underneath. Just don't look at the weights. Kruskal's will require you to do the weight. And now you are building a static library out of it. So you got 2 libraries, okay, one using the other. Finally, you want a makefile. Write a simple main.c. Okay, ask for a file name from the user which will contain some graph. Type in some graph. Okay, manually. Then you call read graph to create the graph and read the contents into the adjacency matrix. Call DFS BFS MST to print the DFS order nodes, BFS order nodes, and the MST in the format that is mentioned out there. You can put some message between this, like the DFS traversal order is something like that to distinguish between them, basically. And then you compile in the makefile. Okay, think what libraries you need. Do you need all of them? One of them? I don't know. Okay, I'm not telling you. So lots of small C files to write, but basically everything that you know. If you have not written them, you should practice them anyway. Once you have got everything, build those libraries, write the .h files. Okay. Build those libraries, write the make file. So 3 make files and this actually 5 .c files and 5 .h files. These are output. Is it clear? Am I clear? You should read the thing details later on. But basically what you have to do.
Sir,
Yes, no?
in the last part,
Mm-hmm.
We are taking in the name of the input file as an input from standard input.
Keyboard, yes, standard keyboard.
Okay, sir. And then we are using that input.
Yeah.
We are assuming that the file is in the same directory.
Yes, yes. All those things as well. Yeah.
Okay, sir.
Okay. Now again, kind of think of, in the process of writing all these .c files and so on, do not lose track of what you are trying to do. Okay. You are trying to simulate an environment. There is one set of people writing one library. Another set of people writing a separate library that uses the first library. This is one-way dependency. And then there is the application writer, which requires only the second library. Okay. And then how do I export the functions from the library? I give you a .h file, which contains these type names. Okay. So you have to use the name heap. You have to use some heap is actually something that we are not using. We are just asking you to write it because just to show you that your library need not only contain that your application uses. It may contain something else because the same library may be used by somebody else using heaps, but not using stack queue maybe. Okay. Like a library of basic data structures. But then whoever uses this, that may be another function in another library or your application main function, whatever. Only thing you know, you have to include the proper header files. And the only thing you know is that there are types called this. So you can declare variables like list, x and so on. You do not know what is inside list. This is an abstract data type. You do not know that this linked list is implemented how, what is the node structure or anything. Okay. And then you can call functions on this. So then now you can say x equal to create list. Okay. Now I got that x. I can say in this case I've got a node. Also I've told you that I will give you a node. So I can say node star x. Okay. And I can say x. Okay. No, sorry, cannot be x. Let's say p. Okay. And I say p equal to search list. Okay. I have got the list here x. Okay. And the value out there. So this is a list stage. This is the return value list. So I've got the proper return value. And I'm just getting the pointer to the node.
Sir?
Yes.
Can we use C++ for this assignment?
You can, but what is your benefit?
No, just the maybe we could like to use C out and all, like
C for this very simple reason. Think of the poor TAs also. Okay, so we got compared to other years, we got very few TAs. Okay.
Okay.
So making things uniform helps them. If you know C++, you know C basically. Let's write in C. Okay, because we have given you, let's write in C.
And don't use that STL library.
Let's keep it in C only. Yeah. I know we can do C++ without STL. Let's keep it C only. I think all of you know it, right? Yeah.
Okay.
So now going back to that question that somebody asked. So since in this case we are using it only for Kruskal's, okay. So when you find this thing, okay, you will get back a pointer. If these are two different nodes, two different routes, the pointers will be different. The same route for the two find calls, the pointer will be same. So comparing the value and comparing the pointers will be basically the same thing. So Kruskal will work fine just comparing the pointer. You don't need to know what is inside the node pointer. Okay.
Yes.
Yeah. There is one small thing I'll discuss with AD. Okay. So got the idea. I will discuss it right after the class, and I will upload the thing. AD will upload in Moodle.
Moodle is fine, but because anyway they will submit in Moodle. No
Right.
other submission. So
we'll upload in Moodle by in another couple of hours max. Okay, so we had a very long class, but that's the assignment. Given you 2 weeks, is it okay? Let's start, then we'll see. But again, my request to you is don't dive into the assignment directly. You have learned Make today. Okay, I'm hoping that you have been practicing GCC. So those things are you are familiar with now. But write small files to do things with Make first. Very simple things, plus finding mean, finding max, simple things. So you get used to the Make, how to write things, how to do the dependencies and so on. So the purpose of this is actually to do Make, but we want to make you write everything because then you get a feel of a complete package and you can actually run the application, see it working and so on. So let's start. We'll have 2 weeks and then we'll see. Okay, so I'm done. If there are any questions, we'll answer. Otherwise, it has been a long class.
Submit a zip file of all the.
We'll tell you the submission instruction.
Okay, sir. Okay, sir.
Exact submission instruction, how to package them and so on. We'll tell you exactly. Anything else? Okay, if not, thank you. And again, we are there. Your TAs are there. If you have any questions in the meanwhile, ask your TAs. Otherwise, ask us. Okay. Eddie knows I will not be there next week. Okay. So, and between probably 21st to 26th, my email is going to be little shady. You may not get a quick reply. Maybe once a day or something. So, if you don't try not sending me mail between 21st and 26th. But if you do, don't send me anything urgent, okay? Because you may not get a reply. Send to Eddie if you have anything urgent or something, or any questions you can always send to Eddie only. Okay. But again, talk to your TS first. Your TS know most of these things, so talk to your TS first. We'll also send the assignment to the TS for them to look over, for them to answer questions. Okay.
Sir, are comments required? Like, will this code be tested by reading the code, or like output will be tested? So,
both.
like,
okay, you have done PDS.
So we can add comments, right? We need to add comments.
Yeah, that was the last thing I was actually. Thank you for reminding me. I thought of saying that. Okay, you should now start writing code. Okay, will not put any marks on comments, but you should write code which has comments in it. Okay, and I'll start you off. Okay, if you have a file, okay, think of your file. Start the file with a comment on what the file does. Okay, at the top, before anything, before even a single hash include or anything. Say, what does it contain? Simple things, right? Some simple thing. Don't write too much. Contains the following functions for implementing stack data structure. Okay. Then every function. Okay. So if you have, let's say, int s something, add a comment just before it. Okay. With one line description, one line for each parameter as to what they are, one line for the return value. Okay. Rest of the thing is kind of subjective, but let's practice this. top of the file, write some small description, can be subjective, what it is. Comments are always subjective as to what the file does overall. Okay. And then you have this, which is one line description, function to insert into a list. Okay. Then you say parameter, suppose I have said int x, int y, just suppose. So you will say x something, I'm just saying one format, colon, write one line about this, y colon, what is it? And then the return value returns, what is it? Okay. At this time, we will not put any marks on it, but try practicing it. For example, this top description that I do, okay, in reality, basically, this is a very standard thing. It's not only just, so file starts with somebody. So other than this description, you have what is called the change history. Okay, so you'll see a line like this, not necessarily these exact words, created by such and such on such and such date. Okay, and then everybody who changes it, okay, writes one line saying modified by this, what is the change you did? Added the function for insertion. So you read that thing from the beginning, you know, this has been changed 7 times. Okay, and these were the changes slowly. But here you will not do that because you are the only one writing the file. So I don't want a change history, but do the description and do this file thing. And then inside try it basically. Anytime that you are doing something complex, before a for loop doing something, add a one line comment as to what is that for loop doing. But make sure there are not too much comment. If they have too much comment, then it's tough to see your code inside the comments basically. There is no hard and fast rule, what is too much and what is too less, but try. But again, for this assignment, we will not put any marks on that, but you should try that. Any other questions? Okay, if not, Eddie, we can stop, right?
Yeah, I have nothing else to say.
Okay.
Okay.
So class dismissed.
Stop recording.